Hello, everyone. So maybe we can wait a couple of minutes because people are still joining.
Yeah, sure.
Okay. So hello, everyone. I think now we can start because we are already 3 minutes past the scheduled starting. So welcome, everyone. Today we are happy to have Dr. Tarun Kumar Pant with us. Uh, uh, Dr. Pant is currently a senior scientist, SG, and head of ITMP at Space Physics Laboratory in Vikram Sarabhai Space Center, VSSC. He was earlier a research student at Uttar Pradesh State Observatory, which was before when I think it's like before Aries old name. After that, he did PhD from Physical Research Laboratory, Ahmedabad, from 1992 to 1998. Followed by he did a couple of postdocs, first at PRL itself, and then he went to University of Toronto in Canada. And currently he is in VSSC. His research interest include optical and radio remote sensing of terrestrial plasma and neutral environment from ground, rocket, and satellite-based platforms, aeronomy, aeroglow, plasma instabilities, radio, and optical instrumentation. So, without taking too much time, Professor Pant, we are happy to have you here. Thank you for accepting our invitation, and maybe you can go to the full screen mode for your presentation. Your presentation will include 45 minutes and followed by about 15 minutes for questioning and discussion. So, and I will send you a reminder 5 minutes before the scheduled completion. So, Professor Pant, please go ahead.
Yeah, okay. Thank you. Thank you so much. Actually, as you said, no, it's my pleasure to be here on this platform and sharing with you my sort of no experience of working in this area for last few years, or few tens of years rather. And as you rightly said, it's no Aries. It's like a homecoming to me. So I'm very happy to be giving this lecture today. And the way I have oriented my lecture today is to sort of try and give you, the what sort of perspective we have today when we talk of near Earth space. Near Earth space, many people will have many different opinions or different picture when you say near Earth space, right? Some people will think of space with astronauts, rockets, satellites, and then so it means a range of things to different people depending on their areas of interest or their expertise. So I'll try to give you a kind of a perspective from the atmospheric physicist point of view, the way we see this region sitting on Earth, because the Earth is the only object right now, a laboratory which is an active laboratory where we can do our tests, observe, and then sort of compare this with the observations of deep space and other celestial bodies. So I hope that by the end of this talk, I'll be able to give you a flavor of what is happening in this area and what are the new areas that are emerging in this context. So thank you, Aries, for giving me this opportunity. So I'll go ahead with my presentation. As the title says, the exploration of near Earth space. So I thought before I go ahead with describing this space, what exactly we mean by near Earth space. I think we all must be familiar with, or we would have heard the name of a scientist called von Karman. Okay, von Karman was a Hungarian scientist who sort of gave a definition based on aeronautics, basically the applications area, aeronautics and the aerodynamics and the objects that we send to space based on the kind of processes they undergo. He gave a theory, and then based on the theory, he gave a region around 100 kilometers to be the boundary of the space, and the space below 100-kilometer line, he called it as atmosphere. And the reason is very clear. What I'm trying to show here is the red line. Red line is the 100-kilometer line. I have marked it here. And then on the right side, you can understand that why Karman has given this definition. You can see the red line, that is the dashed red line. It's about at 100-kilometer altitude. I would draw your attention to the density, that is the number density. And you can see that below 100 kilometer, the number density of the Earth's atmosphere, it increases almost exponentially. As you go from 100 kilometer down to the surface of the Earth, you see that the increase is almost 6 orders of magnitude. So that's the region where the majority of the Earth's atmosphere resides. That's why this region is more dense, and that's why it is called the atmosphere. And the region just outside this line, that is 100 kilometer and above, there you can see that the number density is again it's decreasing exponentially, and from about 100 kilometer to say 500 kilometer, there is almost another 6 to 7 orders of magnitude decrease in the number density. So above 100 kilometer, you can understand that the density of the atmosphere becomes very rare. It decreases very fast. So it's kind of a rarefied medium, and that is why it is called space. And the near Earth space extends all the way from 100 kilometers to about 600, 700 kilometers. And then some people use it in context of the altitudes where the satellites are there. So that can be up to 1,000 and beyond. So now when we look at the, as I said, when sitting on the Earth, because that is the only place sitting on the Earth, when we try to explore, try to investigate the space, we look outwards, right? We look away from the space and towards the sky. And when we look at the sky, the first thing that comes to our mind is, or to our observation, is the number of stars and how luminous they are. Actually, the number that is spread across the sky, and how luminous they are. Some are more luminous than some other stars. So how do we really understand that in context of Earth, and where Earth is, and where our nearest star, sun, is? So I think to this audience, when I put this slide, you will understand that this is a very familiar slide, which is relation, which is called Hertzsprung-Russell diagram, and based on that, it is basically a relation between the luminosity and the mass of the object or the star, the celestial object, or in terms of temperature. So here what I'm showing is in terms of temperature, the color temperature and the luminosity as compared with sun. So what you see is if you look at the sky, almost all objects follow some sort of a relation. Different objects, according to their masses and the size and the temperature, they follow different evolution pattern, and the pattern or the sequence that our sun-like stars follow is the green one. That is when the temperature is low. You can see that it is at the right hand side of where my cursor is. So from there it evolves as it goes, as it brightens, temperature increases, and then it evolves into a different kind of a star, and its luminosity also increases when compared to sun. So when you look at such stars, sun is actually in the present day somewhere here in this main sequence, which is we know, depending on the age of the sun, we can say that after the 4.6 billion years of evolution, this is where sun is. Okay, and that's where we know that close to 5,000 degrees its surface temperature, and this is the luminosity ratio that is to be 1. So it means all the objects in the sky that we look at, they definitely follow some sort of a sequence. So we can actually, depending on their temperature, the apparent color temperature, we can tell that how bright they would be when we compare with respect to sun, and then we talk about these processes. And sun is actually not alone. Earth, when the sun was evolving, Earth was also evolving together with the sun, because sun and Earth are almost, it is believed that they evolved together. They are made up of the same primordial material which made sun. The same material made Earth. So we can say that sun and Earth, as sun evolved, Earth also evolved over the years, over the billions of years, and they both climbed the ladder together as a system. That is very important. And what you are seeing is that as the Earth, the age of the Earth is almost again 4.5 billion years, but then in comparison to that, if we see that the few hundreds of million years when the man has appeared on the sun, which is very, very small. If I do a comparison, like if you take the whole evolution of Earth to be a 24-hour clock, then the evolution of man in the picture has taken only last 4 seconds. So you can imagine that the extent of our presence on the planet Earth versus the different processes that had been happening on the Earth and which had been responsible for shaping up the present atmosphere, its core temperature, its magnetic field, and the extent of gases that we see around the Earth. It is all a result of the evolution of sun and Earth together. And if we see that in the process of evolution, the atmosphere, the Earth's atmosphere as we see today, it has not always been like this. It means the oxygen dominated, the water dominated, where the hydrological cycle is important, where the oxygen cycle is important for the sustenance of humans, because we ingest we take in oxygen for our survival. It was not always like this. So it has evolved into a secondary atmosphere. In fact, if you look at the evolution of Earth in the previous era, what you will see that from the evolution of the species, living species, the fauna, so to say, Earth has actually undergone 5 major mass extinction events which have eradicated almost 95 to 98% of existing life at those times. And I have tried to give you a flavor of this here. If you see the last 600 million years, there have been 5 major mass extinction events. The first one had been in the late Ordovician period, which was basically due to the sudden change in the continental drift. That was the beginning when the continents started drifting or breaking, so to say. So that was the time when the first major mass extinction occurred. And following that, the second mass extinction was relatively quicker. It was in the late Devonian period. It was only within 200 million years. The first one was in fact less than 200 million years. And this happened because there was a sudden change in the temperature. There was a glaciation because of the activity in the sun, the evolving sun. There was a glaciation, and then a sudden change in the temperature of the Earth has changed the concentration of oxygen in air, plus the CO2 in the air and the CO2 dissolved in oceans. And that has actually led to the species, they could not adjust to this quick change. And because of that, a major mass extinction occurred. And then came the late Permian period, which was supposed to be the biggest of mass extinction so far. People believe that it has actually all the Cambrian type fauna disappeared at this stage. And in fact, all kinds of life that was available till that time, only 2% survived this asteroid impact. It is supposed to be due to an asteroid impact. And then after that, it is believed that there was a sudden burst of species, especially the reptiles. And we know that this is the period known as the Jurassic era. We all know that Jurassic animals also met with a mass extinction later. That is the end of Cretaceous Tertiary period, and that was supposed to be due to a meteor impact. And it's believed that this meteor impact was almost like an atom bomb, which was exploded. Only thing is, it was several hundred or thousands of times stronger than the atom bomb. So it has actually brought in the kind of nuclear winter, which has made it difficult for the Jurassic animals to survive. And then there was a mass extinction, and we reach today, and this is where we are. So you know that the atmosphere, the living species, they have actually survived these major extinction events over a period of 600 million years. Okay, but now comes the most interesting period. This is the present period, which is the period of I call it as the arrival of humans, the Anthropocene era, where humans have started affecting the system. It means we are also an active parameter in this multi-component Earth, atmosphere, ocean, sun system. And in fact, you as you know already, that in last 200 years of our technical development in the industrialization of last 200 years or so, we have already shifted Earth's equilibrium. The temperature has been rising very fast. In fact, we have reached a stage where we have to definitely undertake some decisions globally to curtail the emission, some kind of emissions. Otherwise, the temperature will keep on rising, and the conditions on the Earth will become like a very, very strong greenhouse condition, and then the survival of these living species would become difficult. And in fact, many of these species are already undergoing or becoming extinct. So the question is, the first question that I want to pose to you today is that whether our activities or the humans or the Anthropocene, whether we are causing a change or the sixth mass extinction on the Earth, and if yes, that how is it that we can change it? And it's a very, very important question, that because it is going to change our whole narrative. So far, we have been taking Earth for granted. Okay, but you would have realized that last few tens of years, our narrative is changing. We are already talking about going to other planets, living in other planets, developing conditions in other planets so that we can live there in case the conditions of the condition for living on Earth becomes very, very difficult. So the question is, I want to pose is, are we unique? Like, is it whatever we are experiencing on Earth? Because as I said, right now, Earth is the only system that we have where we have all that we need for our survival. But that is changing very, very quickly. Okay. So I would pose this question and then move ahead with my talk. So basically, this was to give you a flavor of where we have reached today as a result of all that we have done in the past, the recent past, when humans have come into the picture, plus the Earth's evolution when Earth was evolving. It's as a complex system, it was evolving. So I can say that our condition, our planet, sun, the Earth is actually a system. It's a very, very efficient system because it has been continuously supporting this complex structure, a complex life system, the complex cycles, the energy system, and the dynamics. So it is. I can very easily say that it is a most efficient, multi-constituent, complex energy system. And complex is very, very, very important term here. And this has been actually recognized by the scientific community today. As you know, this year's Nobel Prize in Physics was given to 3 scientists. And I'm happy to say that not only that these 3 scientists were dealing with Earth's atmosphere, Earth's atmospheric system, which is a complex system. The citation of the Nobel Committee also reads it. Actually, if you read it, it's very interesting. It says that, I have underlined it in red. You can say that it says, the Nobel Prize in Physics was awarded for groundbreaking contributions to our understanding of complex systems. Okay, so that's what I was trying to impress upon you, that the fact that we are taking Earth as a system for granted, but then it's a very fragile system, complex system, whose equilibrium has been shifting continuously, and so far it has been able to adjust to this equilibrium. So with this, I would like to say that this fact we have to keep in mind today, that our atmosphere, the Earth system, the atmospheric system, is actually a very, very fragile, complex system, which we are affecting very, very, very dynamically as a human species at the fastest rate possible in the history of Earth. Now, coming to space, the present day, this is about the history, the past of the Earth's atmosphere. Now, what is it that we have? What we know about this near Earth space, and whether this near Earth space also experiences these kind of dramatic changes, or undergoing these kind of changes as a result of evolution of Sun and Earth system? I would like to draw your attention to this plot, which is a standard black body curve. You all are familiar with this. The visible radiation, it's maximum. We can see that here it is maximizing, and as we go towards the lower wavelengths in energy and the higher wavelengths, the energy comes down, and then the red curve is actually a black body curve. Just to compare that, how does this compare, the solar radiation compare with a standard black body curve of 5,800 degree Kelvin? And we see that it actually matches very well. So we can say that the radiation that we receive from the sun is more or less kind of a black body radiation. And as I said, it seems that the condition on the earth are such that it is meant to support the life system, to support the living species. Why I'm saying this is actually our experience says that the radiation, as the energy of the radiation increases, that is, if we go from visible to ultraviolet to extreme ultraviolet and X-rays, the energy goes, and the strength for penetration also increases. As you know, the X-ray can penetrate very hard bodies, steel. The surfaces were deeper, they can penetrate deeper. But then if we look at the Earth's atmosphere, it actually just the reverse happens. Here you can see that all the X-ray emission, all the radiation which is there in the form of X-rays, ultraviolet, it all gets absorbed around 100 kilometer, at the most 100 kilometer and above. So as the radiation, all these harmful radiation for living species as it come in from the sun, it gets absorbed higher up in the atmosphere. And only visible and only a fraction of ultraviolet reaches lower below. In fact, visible radiation reaches all the way up to the surface, while the ultraviolet is absorbed in the stratosphere by the ozone. So it appears that the Earth's evolution has taken place in such a way that it protects the Earth system. It protects the living systems which are there in this as a part of this. So not only this radiation which comes in and get absorbed in the space around 100 kilometer, when it gets absorbed, it gives rise to the ionization of the species there. And we also call it the region that is generated as a result of this ionization, we call this as the ionosphere. So the outer space, the near Earth space, is also known as the ionosphere, or the region where we have the presence of plasma. And this is how the plasma distribution goes above 100 kilometer. You can see that the density of the plasma increases as we go from 100 kilometer and above. It maximizes around 200, 250 kilometer altitude, and it decreases exponentially. And how did we know the presence of this plasma? How did we infer? That in 1901, there was a very famous experiment done by scientists called Marconi. Marconi did, what he did was he sent in a radio wave from Europe to US, New York. And via what he did was he sent in a radio wave to sky, and then he saw that he can actually receive the radiation in transatlantic in US, and which is possible only if the radio wave has gone up, has moved up, and then it got reflected from the ionosphere, and it reached the American continent. So.
Excuse me, there is
Yes.
a question. So why are you measuring, I mean, when you are plotting altitude with the electrons, is it the measure of free electrons, or?
It's a measure of free electrons, yes.
Okay, and yes. How that is measured? I mean,
We have actually certain experiments. One is called using a radio wave. You can, when you send a radio wave, the frequency of the radio wave, when it matches with the plasma frequency there, it gets reflected.
Oh, okay.
We get a reflected echo from that part of the sky, and from the frequency of the radio wave, we can calculate what is the density.
Okay.
Yeah. So somebody has written, please move this window. Yeah. So so if as I said, no, in the near Earth space, if we have these plasma particles or the plasma species, then we know that Earth also has the presence of a geomagnetic field. Earth has a magnetic field, a dipolar magnetic field, which is because of the dynamo in the core of the Earth, and it is sort of oriented in the way which is shown in the figure. It is like a standard dipole magnetic field, which with having north and south pole, from where you can see the magnetic field lines emerging and sinking. And this is how the overall magnetic field is configured around the planet Earth. And so now the situation becomes a little complicated, because we have magnetic field, we have plasma particles. So it means we have charged particles as well as the magnetic field in the region around Earth. And as we can understand, the combined action of these two only governs the motion of these charged particles. And even though I said that the presence of this ionospheric region was detected as early as 1901 by Marconi's experiment, we didn't know much about this region until the launch of Sputnik, the first satellite. When we send in into the space, we didn't know. One question was that used to be asked was that from where these particles are actually coming, from where these plasma particles are coming in the region, above 100 kilometers, because we knew that the density is very, very low there. Okay. So what the Sputnik, after the launch of Sputnik, the first thing that was noticed was that the Sputnik satellite, once it was launched into its orbit, it underwent a drag. So it meant that there was a significant amount of background background atmospheric species, which was neutral in nature, and which was capable of inducing drag to the motion of the satellite. And Sputnik underwent that drag, and from there they could calculate what is the neutral background. And they found out that even though we have the plasma species there in the atmosphere above 100 kilometers, the neutrals are actually still in significant amount there. These neutrals are orders of magnitude higher than the plasma particles. So it means above 100 kilometers, we not only have plasma, we have neutral also. And it is actually the neutrals which gets ionized because of the action with the solar radiation in X-ray, UV, and extreme ultraviolet radiation. And that is the one which gives rise to, which maintains this plasma environment there. It also, Sputnik also initiated, our confirmation of the role of magnetic field into the motion of the charged particles or the plasma particles. That was one. And the second factor was it kind of started technical development, which is responsible for the present day navigation, the navigation of satellite and positioning, satellite-based positioning, which we all know as GPS and things like that. So it was actually initiated in 1957 after the launch of Sputnik. And I must say that nearly around the same time, India established around 1962, India established its first center, rocket launching center in India at a place called Thumba, which is present day Trivandrum. It was because of the importance of this region, because of the configuration of this magnetic field. The magnetic field is actually the parallel to the ground. And as I said, because of this unique configuration, the plasma species in the atmosphere, they undergo a very particular kind of motion. And that is why it was felt that in India, we should have a space station situated at Thumba. So it was as early as 1962. And I must say that all the major development in the initial years of the near-Earth plasma or the ionospheric physics, India made a very, very important contribution. And the first contribution came in the form of the confirmation of the ionospheric current at 100-kilometer altitude, that is at near the 1 Kármán line, which is called the Equatorial Electro Jet. It is actually a current at altitude of 100-kilometer, which is near the equator. That is like a place like Trivandrum. So if you happen to be at a place like Trivandrum and if you go to 100-kilometer over Trivandrum, you will experience the presence of this current in a very narrow region around 300 to 400 kilometer in latitude. And this was the first major contribution that came from India. And if we go higher up in altitude in ionosphere, in near Earth space, what you see is that the plasma is actually not uniformly distributed. It is actually what you're seeing, these patches. These are the plasma density inferred by a satellite, moving satellite. These are actually, the strips are the satellite observations, which are polar orbiting satellites. So what you're seeing is that the plasma density is actually enhanced at 2 regions around the equator. So see, if this is India. So what you are seeing is that the plasma density is maximum one north of India and one south of India. North of India comes close to the latitude of Delhi and Nainital. That is, if you're sitting at Nainital, presently over Nainital, you would be having an enhanced plasma density at 200 kilometer. And similarly, if I go south of Trivandrum, I would see that there is another enhancement there. And this is called the Equatorial Ionization Anomaly. This is a very famous process, which is known to be acting in this region because of the presence of plasma and the Earth's magnetic field, the combined action of this. And actually, this process affects the plasma temperature, both temperature and the way the plasma moves, or the way the pressure gradients are developed in this region. Actually, the satellite observations show that wherever the plasma density is minimum, there the temperature is more. You see the enhanced temperature, the temperature is low, and the neutral wind or the dynamics or the wind is more. So it means, and the places where your plasma density is high, you see that the temperatures are high. So it means the very process of magnetic field, the combined action of magnetic field and the plasma species actually is able to affect the temperature and the wind of this region. It means it is able to affect the energetics of this system. So it means the near Earth space is also getting modified as a result of the combined action of solar radiation, magnetic field, and the plasma processes. So it is a very, very important aspect. One very important thing which is related to, which is actually of relevance to us in India, is that if you look at this plasma environment, especially during nighttime, you will see that the nighttime the ionosphere becomes irregular. So it means the ionosphere becomes the small scale irregularities get generated there. These irregularities are something like what you in your parlance you say that viewing is good when you are trying to look at the stars using a telescope, and then you say that today the viewing is good. It means the turbulence in the atmosphere is less, and this turbulence is actually the refractive index change in the medium because of the presence of water. Similar thing happens in the plasma environment also. In the nighttime, the plasma gets disturbed, and because of this disturbance, some turbulence or irregularities get generated, and these irregularities play a very, very important role, and which is of very, very significant implication for satellites. Actually, you imagine that if this is the near Earth space where the turbulence or irregularities have acted, and if a satellite is sending a signal from this place to a receiver on the ground, what actually happens is this receiver or the transceiver on the ground, when it sends the signal back, the signal actually undergoes change because of the change in the refractive index, because of the presence of turbulence. And the signal, instead of getting received at this location, is actually received by the satellite at an apparent location. So it means the positioning has a very large error because of the presence of these irregularities. And it has been calculated, it has been seen that if you look at these delays or these kind of positioning inaccuracies across the globe, it is maximum for the region which is around the tropics. So it means for a country like India, this ionospheric delay becomes very, very important, because we are a tropical country. And this is the region, the tropical region is the region where the range delays are maximum. It can be very, very large. It can be as large as tens of meters. And you can understand that if we have a positioning inaccuracy of tens of meters because of the ionospheric disturbances, then that can be fatal to many of the applications, many high precision applications that these things are used. And that is the reason that ISRO has gone for our own navigation system or our own regional navigation system called IRNSS. We have a combination of 7 satellites which are always above India, so that we always have these link established with the ground, even if some part of the sky or some part of the ionosphere is undergoing the presence of these turbulence, or there is a positioning inaccuracy. Some of these satellites will give you a correct signal, and that is why we have gone for this kind of indigenous system. And not just India, actually every country in the world has gone for their indigenous systems, primarily because of this kind of requirements, high precision requirements. So having told that, now what are the new things that are appearing in the recent years? As I said, these kind of technical applications are there, but from the science side, if you look at it, one thing which is emerging from the current observations is that, which was not realized, was that the processes in the ionospheric region, that is the near Earth plasma, in 200-kilometer altitude, if you see, you are seeing these bright patches. Actually, these bright patches are air glow emissions which are coming from plasma at 200 kilometer, at 200-kilometer altitude. So what was seen by satellite is that wherever these brightness was seen in these emissions, these regions, these bright regions are actually co-located on the ground, co-located with the regions where you have large tropical rainstorm centers. That is, the regions where you have large tropical convection or clouds develop. That is where the cyclones occur. That is the Indonesian region. This is the Indonesian region here. Okay. This is the Indonesian region. This is the Brazilian region, and this is the African region. These are the major, and this is the Central Pacific region, where across the globe, where the tropical convection zones are known, and we see that these brightening of these air glow images are exactly co-located with these centers. So what it indirectly means is that the ionospheric variability is a part of it is actually driven by a process on the surface. As I was trying to tell you so far, that it is the sun which is governing everything, the solar radiation which is governing everything. But now in the new recent observations, we are getting that it is the surface processes, the weather processes are also affecting what is happening in this ionospheric region.
Dr. Pant, 5 more minutes.
Yeah, okay. And apart from that, apart from the solar radiation and the surface processes, that is the weather processes, there is one more component which is very, very important. And that component is the solar wind. As you know, that sun continuously emits energetic particles from its sun, other than from its surface, other than radiation. We receive a continuous stream of energetic protons with other elements, and these energetic protons with other elements, they have sufficiently large energy when it comes in contact with Earth's magnetic field. So this is kind of a schematic. These dots are actually the particles which are coming from the sun, the yellow dots that you are seeing. These yellow dots, when they come in contact with Earth's magnetic field, they compress the Earth's magnetic field because they have the magnetic field also, the solar magnetic field also. It compresses and it forms a magnetosphere. That is the elongated magnetosphere. That what you are seeing here is a protecting layer produced by the Earth's magnetic field. So Earth actually goes inside a cocoon, a magnetic field governed cocoon, which is saving the Earth from direct onslaught of these charged particles which are coming from the sun. These charged particles known as the solar wind. The result is that these charged particles, whenever the solar wind becomes strong, we see that a part of these charged particles end up in Earth's near-Earth plasma, especially in the polar regions. And they give rise to something which we call as aurora. And this is what you are seeing here. What you are seeing in the northern pole, you are seeing the brightness of thermospheric air glow, which is known as the auroral emissions. And the auroral emissions means the solar wind energy has actually come into the Earth's near-Earth plasma. It has entered into the Earth system, and it can affect its composition. You can see that its composition, the lighter species like helium, hydrogen, oxygen gets affected. It gets enhanced. The temperature gets enhanced. When the temperature gets enhanced, the ionospheric thermospheric region, it undergoes a kind of energetic changes. And because of that, large scale pressure gradients get developed between the polar region and the equatorial region. That is the equator, like the place like India, and a polar region, say a northern pole or the southern pole. So such large scale wind system get developed. And you can see this. This picture basically shows the x-axis shows the latitude.
I cannot hear now. Anyone else has some experience? Umesh, are you able to hear the speaker?
Yes. Hello.
Even I can't hear.
I cannot hear you now.
Hello.
Yeah, probably they have some connectivity issue on their side.
Okay, I'm messaging.
We can ask Sumanto. Sumanto, can you hear him?
I think he's disconnected now.
Yes.
He's not there now.
Yes. Maybe he will
Just
try.
he's calling. Just wait. Hello. हाँ boss. हेलो हेलो मेरा नेट भी नहीं है
हाँ दुमका जी आ रही है आप we can hear
हाँ
you.
पंजी का इंटरनेट कहते हैं डिस्कनेक्ट हो गया वो कनेक्ट कर रहे हैं दोबारा
Okay.
ओके
Hello. Hi. Am I audible now?
Yes, we can hear you.
Yeah. So I'm sorry. There had been a problem with our internet connectivity.
No worries. No problem, sir. Could you please share the screen?
Yes, I'll just do it now. Is it okay? It's
Yes,
coming.
yes. Please go ahead. I will let you know where we lost your voice. Keep going. Yeah, this slide only where we
Yeah.
connection
Yes.
dropped.
I'm sorry for this interruption. Yeah. So basically, what I was trying to tell was that, you know, if the auroral region, if the input in the auroral region becomes very large, then you can see that the auroral wind system can affect the equatorial region as well. This is where the equator is. This is where India is situated in these latitude sector. So you can see that this whole thing expands both the northern hemisphere as well as southern hemisphere. So such a process can affect the equatorial near Earth plasma also, even though it is not receiving the energy directly from the sun in the form of solar wind, but it can come from the interaction with the magnetosphere, the Earth's polar region, and then from polar region to Earth's equatorial. One very interesting aspect is for the presence of satellite. If we have a satellite in the near Earth space, then what you are seeing is actually these points on where my cursor is. These are the satellite locations, and what you can see is in terms of Earth radii. You're actually seeing the location is about 4 Earth radii on both sides, day side as well as night side. So what happened was the satellite location, these are the satellite location. Suddenly there was a enhancement in the solar wind. There was a transient, there was a coronal mass ejection, and then a geomagnetic storm took place. This is a famous October-November 2003 episode. And what you can see is this, the emission from the sun, it not only compressed our magnetic field, it compressed it to such a large extent that the location where the satellite was measuring these emissions got shrunk to about 1 Earth radii. You can see that from 4th Earth radii, it can come down to 1 Earth radii. So it means if we have a satellite which is sitting at 4 Earth radii, and suddenly our atmosphere compresses because of the compression from the solar wind and the magnetosphere, our satellite will get exposed to these direct emission which is coming from the sun, and which will be fatal for the satellites. Actually, such things have been observed earlier, and few satellites, we have lost few satellites in this process. And this is just to tell you that, you know, we have quite a few technological systems now which are actually which are prone for this kind of damage. We have satellites, we have solar cell, astronauts doing experiments, space stations, the ionospheric currents and plasma bubbles get generated there, which affect the communication signal. And it can induce the large pipelines which go on the continents to very large distances. There, these induced magnetic field can be generated. And this can be dangerous. Some sort of a static can get developed, and it could prove dangerous. So, so where we are today, and what is it that we are, what I have tried to impress upon you is that, you know, the near Earth space gets not only gets affected from the radiation from the sun, it gets affected by the solar wind which is coming from the sun. Now with the recent observations, it appears that it is also getting affected by the weather on the surface of the Earth. So it means if we want to understand this region very well, we need to have all round measurement from the satellite, from the ground, and keeping that in view. Presently, ISRO has 2 missions in mind. One is the mission for terrestrial atmospheric observations. That is for the observation of near Earth space, as I said. This is called the Anomaly satellite, or Disha. The other one is the Aditya L1, which will be observing the sun at L1 point, because that will give us some sort of a time, in advance prediction of an incoming event. So these are some important developments that are taking place right now. I think in coming few years, we will be in a position to have a all-round view of this region. And in 1995, I would say that in one of the magazines, 159, sorry, in 1959, in one of the New York magazine, one statement was given, and it read that in future years, it may be that the Weather Bureau or some space age equivalent will warn us of approaching magnetic storms, just as we are now warned of approaching hurricanes. So it means basically what he was telling is like what we have a system for hurricanes, we will be needing a system for solar wind or space equivalent of solar wind, like magnetic storms and things like that, because we will have so much of a technological stake in the whole process near Earth space system. And in fact, such a thing is possible today. We have space weather prediction centers all around all the globe. We have a variety of systems which are giving reliable information on the solar wind and then other space-based elements. So with this, I think I have come to the end of my talk. I thought I'll end end my talk with this slide. This is basically the image of Earth as taken by Voyager. Voyager in 1994, when it was very, very far off from our solar system. I mean, beyond our solar system. And you can see that this is where the Earth is. And looking at this vastness of the space, and the Earth has a dot here. The Carl Sagan has written a very, very, very profound sentence, which I will not read myself, but I will let you read it. It is very, very impressive and very, very true. And it gives all of us some thoughts to think. And I think with this, I'll stop.
Okay. Thank you, Professor Pant, for this very nice presentation. Now we have time for some questions and comments.
Yeah,
so
sure.
Yeah, so I encourage the audience to maybe directly unmute themselves and ask the question, or maybe raise their hand and I will point their name.
Yeah.
Okay, so while people are, they will ask the question. Actually, sir, I have one small, see in this picture itself.
Yeah.
Okay, it looks like that Earth is in some street. You see some sort of line.
Yes.
It is like some sort of dust lane kind of. It's a real structure, or it's like some artifact of the telescope instrument itself.
It is, in my opinion, it is partly because of the instrument effect.
Okay.
You see that there are some other lines too. See here.
There is a very famous, should I say, sentence. Okay, that's pale blue dot. It is known by pale blue dot. You just type in Google pale blue dot, you will get to this.
True.
Is Carl Sagan's book. Cosmos.
Yes, you're right.
There, and it says it goes like a pale blue dot hanging in the sunbeam. That's our
exactly.
That's
on a ball of dust suspended in a sunbeam.
Yes.
And
he goes philosophical here that to capture a part of this, lots of kings have come and killed a lot of people, and this is the place where all the people we hate and all the people we love live there. And it's very philosophical. It's a very fantastic.
Very.
At the end of every question answer,
correct.
That would come. I was about to thank you for showing this.
Oh,
it's a very profound statement and a very profound.
Really.
Thought.
True.
About human knowledge.
True.
Okay, thank you.
I have a question, Vidhi.
Yeah.
Please go ahead.
So this is regarding your second live slide. You said in future we'll be warned about activities from sun which will be relevant to us. So
Yes.
apart from satellites technology getting destroyed, or or some other near Earth activities, will in some near future time these be information be relevant to humans as directly more than that?
Yes. I am. I'm very much. I believe that it will be very relevant, because see, right now, as I was trying to tell you in the beginning, right now we see the near surface processes as something which are not getting affected by directly by the solar process, right? That is what we kind of like solar wind or a storm or something like that. We feel that it is not going to affect directly the surface processes. But then what we see in recent years is that the kind of feedback mechanism we are having, especially say in the generation of the clouds. The cloud seeding is done by the cosmic particles, the high energy particles. They act as cloud condensation nuclei. It can affect the cloud coverage. Then a whole sequence of the hydrological cycle. And the induction current, the currents which are generated in the magnetosphere and ionosphere, they have actually a very strong induction on the ground. So, which affect all our processes on the ground. Say, for instance, transformers, the big transformers, they get burned. It has been observed. We haven't seen it over tropics so far, but then the countries in the polar latitudes, they have experienced it over the years many times. The electrical grids have been failed. The transformers have burned. So these kind of things, I think, very much relevant. And if an event which is like a Carrington type event happens suddenly, I think nothing will be prepared to kind of face that, because now we are having so much of our dependence on the space-based systems, right from banking to position to our communication, everything. So I think that will be a very it will be very relevant. That's what my point of view.
And are there, like you mentioned, power grid failures and transformers? Yeah. So are there any safeguard measures being taken?
Yes. Right now there is something called the GIC indicators or sensors. What actually all these countries, what they do is wherever they have these large transformers on the ground, or the very long pipelines which are carrying oil and other things, what they do is they connect these costly systems with these GIC sensors. These GIC sensors are basically induced current sensors. They have Hall sensors in that, and then what they do is they will record or amplify the induced current effects, and they will tell that okay, right now this kind of effect is going on in the ionosphere, and its effect is being seen on the ground. And if it goes beyond a particular value, if this induction goes beyond a particular value, it gives a warning to the systems, and they switch off. They switch off the transformers.
Thank you.
Yeah.
Thank you so much.
Any other very quick question? If not, so let's thank Dr. Pant for a very wonderful talk and very nice giving the overview of near Earth space. So thank you, Professor Pant, once again for accepting our invitation and giving us this seminar. We hope that sometime in future, when the things will normalize, you will be able to visit us here in Aries. so that we can have in-person discussion.
Oh, thank you so much. It was actually my pleasure. It was so nice that you thought of me and gave me an opportunity to talk to you, and then give this talk. So the pleasure has been all mine. Thank you.
Thank you. So thanks everyone, and then we will see next week then. Okay. Bye bye everyone. Have a nice day.
Bye everybody.